We're going to talk a little bit about the fundamentals of design and engineering and go through the process of putting together a single-story self-storage so that you can see the project from the aspect of the designers and the engineers. Metal building design and engineering is contingent upon the specifications of project architects and engineers. But their specifications are based on code requirements. And code requirements come from a lot of different places. But the predominant code that everyone follows right now is the International Building Code plus the local codes that apply to your project. The latest version of the International Building Code is the 2006, but this one has some excellent pictures that we're going to be using for our presentation. The design team that works through all of these codes, finds out what they are and how to apply them to the project, are the civil engineer, the architect, the mechanical engineer, and the structural engineer. And they all work together in creating the project. The responsibilities of the civil engineer are basically for everything with regard to the land and the utilities, but not the buildings. Once the buildings start, the civil engineer's work is finished. But they are very, very important in finding out what all of the codes are, what the zoning is, if there are any watershed problems, and what soil problems could be anticipated. The architect is the person who has the ultimate design responsibility for all disciplines. All of the other people working on the project report to the architect. In addition to coordinating everything, they also draw the site plans, the architecturals, and provide the renderings. The site plan is just a master layout for the entire project. This is a site plan and a finished building for the same project. The site plan gives everyone who's working on the project a visual representation of how the whole thing is supposed to lay out, how the buildings all fit together, the way the roads go, what the different setbacks and things are, the different things that have to be taken into consideration when we're getting ready to go through the project. The architecturals are actually the instructions for construction. And all of the other disciplines go off the architecturals in designing their own individual portions. This is a cross-section, this is actually an elevation from one of the design drawings. The plot plans, the floor plans, the elevations, the cross-sections, and the details are the basic footprint for the whole project. This rendering is the architect's visual representation of the project, and this is very important when you are going to a zoning committee or neighborhoods so that you can tell them that the project that you are anticipating building in their neighborhood is something that they can be proud of. And this is something that the architect provides for you based on the plan that she has designed. The MEP engineers are the mechanical, electrical, and plumbing engineers. Mechanical is your air conditioning, and they provide all of the details for their particular disciplines so that all of the construction can be coordinated. This is a simple drawing of an HVAC duct. As you can see, the mechanical engineer would have designed how the duct is to fit in the building, and then that's the actual application of the design. The interfaces that have to be taken into consideration in self-storage with HVAC considerations are the space for air handling equipment. Where it's going to be placed has to be part of your metal building design and engineering, the units themselves and the ducting. You have to make sure that there's plenty of airflow above the hallways and above the partitions, and how much airflow is needed is dependent upon the HVAC design. The insulation type in walls and below the roof deck is part of the HVAC consideration, and you're going to have air inlets in the exterior walls, and there are going to be condensate drains. These things aren't part of the actual metal building, but you have to be aware of them and take them into consideration when you're actually designing your building. Electrical items have to be taken into consideration as well. The exterior fixtures, for instance, can't be in the same spot where you're planning to have a downspout placement. Downspout placements are set at specific intervals in order to handle the water coming off the roof, but we have to coordinate with the electrical to make sure that their fixtures and our downspouts aren't in the same place. There are also considerations for soffit heights and lighting fixtures in the hallways, equipment rooms for electrical or panels, and conduit placement. All of these things from the electrical portion of the drawings can have an effect on the metal building drawings as well. Plumbing considerations are very minimal, but you just have to be sure that there are no pipes that are located coming up in the middle of a unit or in the middle of a hallway when you're drawing your building. And sometimes downspouts have to be tied in to underground drainage, which can be handled by the plumbing details as well. Fire safety is something that comes up all the time in your metal building design. If the building is going to be sprinklered, your partition wall height may be different. They may want to put in mesh, which will also affect your partitions. And partitions oftentimes have to tie into firewalls that are made out of building materials. And there's a coordination of trade efforts that has to take place because you're needing to tie in your walls, which are throughout the building, with other trades. So everything has to be designed so that both trades know exactly what they're supposed to do in these different intersections. Oftentimes there are also smoke evacuation fans that are put into the exterior walls, and these are usually placed by the people who are going to be putting in that smoke evacuation system, but the metal building contractor is the person who is going to actually be making those holes most of the time. And these should be detailed on the drawings so everybody can be coordinated with what they're supposed to be doing. The structural engineer is the engineer that we're going to be talking about most today. They are responsible for the design of the building itself and the integrity of the building and the material specifications that are going to provide that integrity. The most important design factors in structural engineering are loads and stresses. Loads can be dead loads or live loads, and stresses are compression, tension, and shear. Live loads are people, furniture and fixtures, storage goods, movable items. Basically anything that comes into and out of your building that is not attached in some way is part of the live load. Building codes dictate how to cope with loads and stresses. Stresses really are basically a response to the load. The loads that have to be considered in addition to live loads and dead loads are forces of nature. Wind loads, snow loads, rain, earthquake, flood loads, all of these are taken into consideration when the engineer is making their calculations. Self-storage falls under lightweight storage in the International Building Code, and that means that it has to be able to withstand a load of 125 pounds per square foot. An office space load is only 70 pounds per square foot, and a residential space load is only 40 pounds per square foot. So in the lightweight storage load considerations, they're taking into consideration everything that people might be able to bring into the building and its weight. The International Building Code is instructions, tables, and maps. And these put together give an estimate of the requirements to withstand loads and stresses in different areas. Building weights, occupants, contents, and resistance to forces of nature are all built into the maps and codes. The International Building Code publishes zones in the forms of maps. Examples would be wind ratings, snow loads, and seismic lateral loads. This is an example of a wind load map. It shows the entire United States, and then there's a close-up here of Texas because we have hurricane force winds. The IBC goes into great detail in estimating what the anticipated loads would be for any particular area, and the structural engineer has to design his building for what the IBC estimates are the potential loads. Snow loads are mapped out in the same way. Seismic loads are as well. And I put in a close-up of California there because it's a very seismically active area. And you can see the difference between the eastern half of the United States and the western half of the United States. Anything west of the Rockies, there are very detailed seismic zone loads. Stresses are the internal characteristics of a material to resist those external forces. Tension, compression, and shear that we mentioned earlier are the material's resistance to the different loads that we've talked about. They are a component of the load calculations. Tension is the stress to pull something apart. For example, if you have a severe wind coming toward your building, it's going to be pushing against the building and pulling the roof upward. It's also pulling the air out of the building, lifting upward on the roof. This is the tension to pull something apart. Compression, on the other hand, is the stress to push things together. The heaviness of the physical weight of the building sagging down upon itself is called compression. Shear is a lateral force caused by wind, and it's countered by the diaphragm bracing of your building. If a wind is coming from one side, it's pushing the building in one direction. The opposing parallel force of the building itself is to pull it back into alignment. That is an example of shear and lateral force winds. The International Building Code describes all of the codes that are required and provides tables for all of the elements that need to be taken into consideration in designing to compensate for the loads that are potential for your building. When they do that, they design the members or the pieces of material that are going to accomplish the requirements needed for the code. One of the things they take into consideration is deflection, which is the amount of sag that a beam has under load. Sag is determined by the size of the beam and the geometry of the beam. Deflection requirements are also stipulated in building codes. A lightweight storage code format is 1/240th of length. That's the way it's written in the code. What that means is that for each 20 feet of dead load, you can't have more than 1 inch of sag in the beam. Elevator lobbies and office areas that aren't supported on a smaller grid system where there are longer stretches of open areas, they need to have stronger beams to prevent that deflection. When construction drawings are done, the codes have directed the architects and engineers' drawings and specifications. The implementation of their design and the engineering requirements is carried out through the individual trades. It's the individual trades that do the construction drawings, and also their erection techniques have to follow the requirements set out by the architects and engineers as dictated by the codes. Slab requirements are also based on anticipated live and dead loads. A single-story slab load would be 125 pounds live weight and 50 pounds dead weight per square foot. This is important because when self-storage is built, it's built on a 5x10 grid system, and that spreads that load out evenly over the entire slab. The composition of the soil and the topography of the soil also affect the slab design. When you're designing the metal building, the features incorporated into the slab have an effect on your materials. Brick lugs, step downs, entries, elevators, all of these affect the type of material that you're going to use and the lengths of materials that you're going to order. The building basically fits between the slab and the roof line. The roof line follows the slab in unison to changes in the topography. This is a step-down roof and a step-down slab, and you build your building between that roof and that slab, and all of the parts and pieces have to be measured to fit within that area. Construction metal building materials are selected to meet the code requirements that are incorporated into the design. And there's really two types of materials that are used in self-storage. There are pre-engineered materials, and there are materials that are designed per use. Pre-engineered are components that have specific designs, specific weights, and you just order them off the shelf like you would Tinker Toys. Designed per use are like I-beams that are designed for specific spans with specific deflection. And it's usually a combination of these that is used in most self-storage projects. Each of the components are rated so that they can be selected to meet the specific code requirements. So when you're picking up one of those Tinker Toys, you know exactly what those properties are and how they're going to fit into the code. When you actually start building your building, we start with vertical studs. They're affixed to the slab, and they support other components to brace the building. And this is an example of studs laid out on that 5x10 grid that we mentioned. These are Cee Columns, 4x2, 16 gauge, and they exceed the lightweight storage code requirements. And that's what we're looking for, something equal to or better than code requirements. On a 5x10 grid, there are 50 square feet per unit. According to code, each column has to carry 20 pounds of live load and 5 pounds of dead load per square foot. That 50 by 25 equals 1,250 pounds of load-bearing capacity that is required per column according to load. The C's that are generally used in self-storage, the example that we use, the 4x2s, they carry 3,000 pounds each, so they are more than double what the code requires. The grid is placed on the slab with string lines so that we can position these columns appropriately. The intersections are where we put the clips, and the clip that's shown in that intersection is what the slab attaches to. Around the exterior of the building, base channels are used to support the studs that go along the outside edges. At mid-level, we also put a girt. A girt is an attachment point for outside sheeting, and it can also be used to support infill bracing if you're going to have some type of exterior coating or firewall. And the girts, the exterior channels, and the studs are all part of the framing of the building. On top of the studs, this is where the purlins are attached to support the roof and the upper floors. And the purlins complete the framing part of the building. Purlins run longitudinally the length of the building. Connection points for the purlins to these studs and the types of fasteners that are used are all part of code and all part of the building plan. Everything is very detailed to make sure that the integrity and strength of the building is consistent. There are two types of piers. Piers support the roof at the eaves, and they can also form the exterior wall of the building. They serve as jambs for outside doors as well. Metal piers attach to slabs with wedge anchors through the pier and into the slab. And masonry columns are built with the dowels that go all the way down into the cement or to the concrete. Both types attach to the eave strut with self-drilling screws. So that's how the piers are attached to the eave struts around the exterior of the building. Masonry columns are a little more sensitive to breakage, so we use pre-drilled eave struts and wedge anchors when we're attaching the eave struts. Partitions are the next thing that are incorporated into the building, and partitions can actually go up in conjunction with the framing because partitions provide diaphragm support for the building. Partitions and the roof are the two things that actually give the diaphragm bracing. Insulation provides thermal and moisture barriers, And that's usually integrated into the design. In this example, you can see that we have chosen 5-foot wide insulation rolls that fit directly into the 5-foot grid pattern. The bottom example is the back side of an exterior wall panel that is a rigid insulation that has a panel on each side. There are variations in the types of insulation that you can buy, and there are more and more variations all the time. Basically, insulation has a facing, which can be a panel facing, foil, vinyl, or polypropylene. Vinyl is only used if it's not going to be seen and not exposed to sunlight. The materials that insulation are made out of are fiberglass, bubble insulation, and rigid foam insulation. Radiant barrier values are part of code requirements, the same as our metal construction pieces are part of code. Insulation selection is based on our value as well as the cost and the design options you have. Exterior doors have to be wind rated to maintain the building's structural integrity. If you remember the slide that we showed with tension where the wind is blowing in against the outside of the building and lifting it up, the example of the doors that are bent were from the hurricane that came through Galveston. And if the doors blow out, that ruins the integrity of the building. So they have to be wind rated the same way as the rest of the building is wind rated by code for that particular area. On the interior hallways, when the design is being done, they're usually a 5-foot width as a minimum, and you have to allow for the interior hallway system, panels, headers, soffits. All of these little things have to be taken into consideration when you're designing on the 5-foot grid. An inch does make a difference when you're designing in self-storage. For the recessed entries, things that you have to take into consideration are door swings, clearance, the type of insulation you're going to use, what type of surface is going to be on the entry, the lighting, and if you're going to have an exterior soffit. Entryway doors and exterior decorations have to be able to withstand the forces of nature as well. The most significant factor in tension is determination of the roof wind rating. This rating is determined by code, and the gauge of the roof, which is the thickness, increases in proportion to the wind ratings. The number of fasteners used and the type of fasteners have to have a wind resistance capacity equal to the roof. Roof hatches also have to be wind rated. If a roof hatch blows open, it can suck the air out of the building and lift the roof right off. Roof hatches are very important as a safety measure, but they are a potential problem if they're not installed right and wind rated correctly. A standing seam roof has to have at least a 1/4 inch on 12 pitch in order to shed water. Screw down roofs require at least a 1/2 inch on 12 pitch. And what that means is that for every 1 foot of length, it has to rise either a 1/4 inch or a 1/2 inch in order for water to shed off. This picture is a gable roof, and of course that's a much steeper pitch. Water control is absolutely the most important factor in roofing materials. The roof panel, all of the closures that are used, the rake trim, ridge flashing, gutters, downspouts, all have to be integrated correctly and sealed correctly in order to maintain their integrity to repel water as well as their structural integrity. A positive slope has to be maintained throughout any transition on the roof line. If you recall, the roof line follows along in unison with the slab, and sometimes they're at different levels. Any transition that you have from one level to another to follow topography, or in this case where it's next to an elevator, positive slope for watershed always has to be maintained. Another important consideration is the size and placement of gutters and downspouts. You have to take into consideration those environmental factors, temperature and precipitation amounts, when you're determining gutter and downspouts. Another factor of metal building design and engineering is architectural accents. Often accents are made with other materials, but they are framed with metal framing. Accents can basically be done one of two ways. They can be integrated into the building themselves, or they can sit as an envelope on the outside of the building. In this case, the frame is sitting on top of the roof, where in the previous case, the accent was integrated into the actual building itself. In this case, it's added on outside the envelope. The framing for this roof is actually on top of the structural roof. Accent and designed materials have to meet code standards. Thoughtful metal building integration with all of the different types of external coatings that can be applied is essential to having an attractive, weather-tight product. Metal building design and engineering incorporates all of these codes to assure personal safety for everyone that is using the building and long-time structural integrity to maintain the value of your product.